Welcome to the Problemers Channel Season 3, Episode 46, the episode which I titled Where Do Mathematical Problems Live for Earth-Moon Equiangular Orbit, because in this episode we will not even scratch a surface but simply acknowledge the existence of a very important, fundamental, and quite vast layer of human activity called problem construction. But before we deep dive into the underlying details of that process, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from the material that we present on this channel is for you to go to the homepage of our channel, and at the top of that page in the channel's trailer section find the episode titled The Problemers Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel in a lightning round, who we are and what we do. On this channel we solve problems in mathematics, physics, and computer science in a happy and a never-ending chain. If you have any questions, then by all means do ask. The best way to ask your question is to find an episode on our channel that resonates with you and use the comment section under that episode, and I will take it from there. And of course, and as usual, I would like to extend my deepest gratitude to all the current subscribers and current supporters of our channel. And before we begin, another small announcement, because lately I'm being asked on a regular basis still, how do I use this channel? In addition to the video explanation of how to do it, I've put together a written document called How To, which I hope will be useful for both the newcomers and the veterans of our channel. Alike, the link to this free PDF file is in the comment section to this episode, and this file puts into one convenient place an ability to look at our channel in general and get a good comprehension of, again, who we are and what we do. The objective of the mathematical problem S3M25 was to come up with a problem that is based on a, not the, but a definition of an object that many of us get to know from early childhood, a circle, because starting with this episode, I want to not even try to scratch the vast surface of the art and the craft of constructing technical problems, but I want to acknowledge the existence of this vast and fundamental technical layer of human activity, because my claim is that any time that you spend on trying to construct an interesting problem, even if that attempt ends in a miserable failure, is a time well spent, because the process of constructing a technical problem is just as, if not much more educational than the process of solving technical problems. And just like with any human endeavor, the ability to create elegant, beautiful, crisp, and juicy problems requires special sauce whose ingredients are experience, patience, taste, judiciousness, knack, and of course raw technical knowledge of the local material. And here the last ingredient of the special sauce is a necessary but not a sufficient requirement, because quite a few people are in a solid control of knowledge of their stuff, but not many people can put together such beautiful, crisp, elegant, and juicy problems. So knowing your stuff exceptionally well is necessary, but not sufficient in order to be able to come up with an interesting problem. And It is interesting that starting from middle school, high school, and moving on to college, pretty much through your entire college career, we concentrate most of the time on solving problems. But a sobering question over here is, where do these problems come from? Well, so far, up to, let's say, around 2025, 2026, all such problems that you see in all textbooks in middle school, high school, and college, they are not shipped to us wholesome from a parallel universe by superior beings, but every such problem was put together by a person who precisely possesses this special sauce and can put this such a problem together. To that end, I put this episode together for you so you can try your hand at the process of constructing an interesting problem, and you have something to think about in your spare time. Now, the problem that I gave you is very open-ended, of course, and as we shall see in a few seconds, a circle has many different faces, but so far up to this point, if you're watching this episode, you have at least two hints. The first hint I gave you at the end of the previous episode, where I suggested that you think about the following an idea. Can a geometric point be a circle, and conversely, can a circle be a point? And the second hint that you have is the title of this episode, an Earth-Moon equiangular orbit. So in order to make it as a fun and friendly intellectual challenge, as this episode develops, as we move along, try to see where are we going with this, and exactly how we will put that problem together. When you write or produce video content for a very diverse audience that has varying levels of mathematical maturity, mathematical skills, and mathematical knowledge, it is very difficult to judge which problem is very easy and which problem is very difficult. So in order to balance these two extremes together, first I would like to go over a not complete list, or not a complete way of defining a circle, in order to show that the object that many of us are very well familiar with has many different faces. And to that end, the very first potential definition is perhaps the most popular worldwide. This is what most children see in their, let's say, middle or high school, and then they promptly forget about it. But this is the classical definition, that a circle is a set of all points in a plane that are equidistant from a fixed and coplanar. This is important to mention in your definition. Coplanar point called the center of a circle. And after that, we have more possibilities. For example, the second potential definition of a circle is the set of all points in the real plane, x and the y, that have the coordinates x and y, and these coordinates satisfy the equation shown over here: x minus a squared plus y minus b squared equals r squared. Here again, x and y are the coordinates of that curve, to which we refer as a circle. A and b are the coordinates of the center of that circle, and r is the radius. And by that algebraic way to define a circle, it is evident that we hang all of our hats on the fact that this equation is given in the traditional Cartesian x or y coordinate system. But if we were to give a similar definition in the polar coordinate system, then this expression will be quite different. It will be r squared minus 2 products r times r0 times cosine of theta minus theta 0 plus r squared equal a squared. Here, a is the radius of the circle, r and theta are the polar coordinates of each and every point that belongs to the curve in question, a circle, and r0 and theta 0 are the polar incarnations of the center of a circle, which in Cartesian coordinates we have as a and b. Yet stepping out of the real plane into the complex plane, one way, but not the only way, to define a circle is with the following algebraic expression, and to claim that a circle is the set of all points in the complex plane whose coordinates z satisfy this equation, the modulus of z minus c equal to r. Here r is the radius and c is the complex number, again with two components, real and imaginary, that fixes the location of the center of that circle. So that's number 4. Next, if we parameterize our circle over the trigonometric functions, then we will define a circle as the set of all points in the real plane that have the coordinates x and y such that x is equal to a plus r times cosine of t and y is equal to b plus r times sine of t. Here again, a and b are the x and y coordinates of the center of that circle, r is its radius, and t is the parameter that varies over the subset of real numbers from 0 to 2 pi. Let's say 0 inclusive, 2 pi exclusive. But if we parameterize our circle over rational functions, then the very same circle can be defined in the way number 6 shown over here, where again it is the set of all the points in the real plane x, y such that these coordinates satisfy the following relations: a plus r times 1 minus t squared over 1 plus t squared, and y is b plus r times 2t over 1 plus t squared. Here t is a parameter that has to vary over the entire set of real numbers and plus the point at infinity as a technical wrinkle. Yet another way, this is a fun definition, number 7. Pretty much if you're in middle school, high school, or even I would say you completed first and second year in college and did not take a even introductory course in topology, this will be a fun definition because you will be able to read each and every word in this definition, but you will have no clue what all these words are. In other words, according to a topological definition of a circle up to a homeomorphism is a compact, connected, one-dimensional manifold without boundary. So here in this definition, this is actually a good example of how grown-up mathematics works, because even to comprehend the definition, not to figure out how to do some complicated task, like for example compute or put together the automorphism group of a certain group, but here just to understand a definition you will need to spend several good weeks or perhaps even months, because at this point, again, like I said, if you're in middle school, high school, or first 1, 2, possibly even 3 years in college, you will not know what homeomorphism is, you will not know what a compact set is, you will not know what a connected set, you will not know what one-dimensional means, because most likely you think you have an intuitive understanding what one-dimensional means, but in reality, upon further investigation, your intuition is off. You most likely do not have the correct understanding what one-dimensional is. You do not know what a manifold is, and you do not know what a boundary is, but still, this is a topological one. Perhaps it's not the only one, but a topological definition of a circle. Yet, as a definition number 8, a circle can be defined in terms of conical sections. And over here, the definition may feel a little slippery, but look at this. A circle is the result of the intersection of a plane perpendicular to the axis of a cone of revolution. Here it is tempting to say that this cone is a right circular cone, but if we say that a circle is the intersection of the plane that runs perpendicular to the axis of a right circular cone, that will be what? That will be a circular, pun intended, definition as such. The cone in question is the cone of revolution. And how is it generated? A cone of revolution is generated by rotating a right triangle about one of its sides, not the hypotenuse, but one of its sides, or one line segment that is orthogonal perpendicular to the other, around this one or around this one. Next, a circle can be defined as a specific case of a more generic curve, an ellipse. In other words, a circle is an ellipse whose two foci coincide. This is one way, and an ellipse can be defined in a non-circular way using its, for example, optical property. So we do not have any circular line of reasoning in our definition. Another way to define a circle by an ellipse is to say that one of its, or maybe both of its axes, right, this one and this one of this, or both, were continuously transformed to a point where when their length are the same and they match, let's say, the specified radius. So squeeze for example, the large semi-axis to the point that it is equal to this one, or maybe stretch them continuously, stretch this one continuously, basically make an ellipse, turn an ellipse into a circle, and that process of a continuous transformation of a circle into ellipse, or maybe even the other way around, an ellipse into a circle, is used in physics, for example. Now, the next definition, that was a definition number 9. One more definition that I want to put in front of you is a definition number 10, is the following. Technically, this will be called an integral curve, but we can define a circle again as a curve, as a planar curve. That is the integral curve of this differential equation over here. And this differential equation is quite transparent. This is a baby equation with separable variables. We separate the variables, integrate y squared is equal to minus x squared. We multiply this thing through by 1/2, and then we move minus x to the other side of the equal sign. So y squared plus x squared is equal to certain constant. Guess what this constant is? The meaning of this constant could be, for example, the square of the radius. Now, this differential equation actually also defines a circle, believe it or not, but it may seem way too complicated for a definition. Let's go over this differential equation. In the numerator, we have 1 plus the first derivative of y over x, of course here, over x squared, and this sum is cubed. Look at this. This is a wild collection of exponents. In the denominator, we have the second derivative of y over x, and that second derivative is squared. And all this beautiful mess is equal to r squared. Here you can quickly figure out that r is the radius of that circle, and the question is, where on earth did this differential equation come from? Well, this is a separate exercise. I recommend that you try to undertake it. If you take the origin, the equation of an origin-centered circle, x squared plus y squared equals r squared, then that origin-centered circle, the equation of that circle, can be morphed precisely into this here differential equation. So as you can see, a circle, as I claimed a few seconds ago in the opening image of this segment, has many different faces. This is not by all means the exhaustive list. There are other ways to define a circle, but this is just to show you that there is a open-endedness to the problem that I gave you, and that will hopefully present a challenge. Now, in order to make this problem more manageable and help you hone in on the problem that we will formulate eventually, the Earth-Moon equiangular orbit, the problem statement in this case will be the following. Find the trajectory or the orbit from each point of which both the Earth and the Moon are seen under the same angle. And in order to hone in on the construction of this problem, we will use yet another definition of a circle that I did not show so far. And to some extent, if we will try to partition these definitions, for example, we can somehow, under a fairly tight artistic license, say that the first, let's say, 6 definitions are based on this here metric definition of a classical definition of a circle, and they have the spirit of equidistance baked into them. The topological or atopological definition of a circle that you see over here doesn't seem to have this equidistant idea baked into it. The conic sections definition also is kind of free of this, and the definition of a circle that is based on the solution of differential equations also seems to be free from this equidistant idea. But a definition of a circle that is of interest to us and around which we will construct our problem is the definition that goes back to about 2,000 years ago. It belongs to an ancient ancient Greek mathematician Apollonius. And according to this definition, a circle is basically a locus of all points in the plane. The ratio, you see, not the distance, the linear distance, the classical metric, if you will, but here is the ratio of distances from each point to two fixed coplanar and distinct points is one and the same and distinct from zero. So if we take any point of, let's say for now, a mystery curve, this point right here or this point right here, and then we measure this distance and this distance, and let's say we will mark this distance as d1 and this distance will be d2. We will say d1 over d2 will be exactly the same as this distance. Let's say this distance is d3 and this distance is d4. So this ratio will be the same, d3 over d4. And under the assumption that this ratio k is distinct from 1, when this ratio is precisely 1, we will see what's going on over here. The structure of this locus is very well known to you. You will figure out what it is. But it is also important that we agree that these two generating points, let's say our proverbial points A and B, are given, they're fixed in the distance between them, and they are distinct. And before we can put our problem together, let us see how this definition of a circle, known as a circle of Apollonius, comes together. Algebra. Now, as we will dive into the details of the underlying material and undertake all these proofs that we're about to undertake, I can already anticipate what's going on through your mind just about now. You're thinking, Roman, why are we doing all these things? Why can't we just cut to the chase? Well, the answer to the question is the following. This is precisely the crux of the matter. This is precisely how technical problems are born. This is a plausible path, and in my experience, it never ever happens that one day you wake up and out of the blue into your mind in pops a beautiful, crisp, deep, elegant, juicy, tasty problem. And if you think that I'm wrong, I'm more than willing to hear your story. If you think that you can wake up one day and out of nowhere with zero effort create an interesting and deep problem, then share this problem with us in the comment section. Share a little bit of a story of how did you come up with this pearls of mathematical wisdom. Meanwhile, again, in my experience, the only way to come up with something that even remotely interesting and meaningful is to get up close and personal with the local material, and this is precisely what we will do across next several segments. And this is basically the manifestation of the simple truth that your appetite comes during the meal. In my experience, when you study this or that material, it is sometimes so happen that an interesting idea or a branch of an idea, something that you can investigate, this idea pops into your mind all by itself and seemingly out of nowhere. Now, how does that happen? That part is a mystery to me, but this is basically the motivation of everything that is about to come. The only practical way to come up with an interesting problem is to step up to the plate and get close and personal with the local material, because only while we chew on this material an idea may come into our mind. That's number one. Number two, the good starting point for this investigation of how a definition of a circle due to an ancient Greek mathematician Apollonius comes into existence is Euclid's Elements, Book 6, proposition number 3. Proposition number 3, again, we should understand that the way things work in mathematics is all mathematical knowledge is strictly hierarchical. Every theorem sits in the so-called dependency graph or dependency tree, and sometimes a path to a particular theorem is quite convoluted and complicated. All these theorems start at a set of axioms, and then they rattle their way through this dependency graph. Somewhere over here is our theorem. We should understand all that. So evidently, This is book 6, proposition 3, and what happened in the previous 5 books with the tons and tons of interesting theorems. So in some sense, yes, if we want to start from the beginning, but this is again being too pedantic, that much we understand. This is a reasonable starting place that will keep the size of this episode manageable. So we will start with Euclid's Elements, Book 6, Proposition 3, thanks to the monumental effort of Dr. David Joyce. All this information is available to the public free of charge. You can find the links, read the proposition for you, and the essence of this proposition comes down to the following. I put the very succinct version of this proposition into the title of this segment: if bisector, then same ratio. And here the deal is the following: given a triangle ABC, non-degenerate, planar Euclidean, yada yada, we know the drill. If an internal bisector or a bisector of an internal angle of such a triangle is constructed, and D is the foot of that bisector. Let's say this bisector emanates from the vertex C of the triangle. Then the claim of this theorem, actually, this is a two-sided if P then Q implication, which says that if CD is the bisector of an interior angle of a triangle, in this case C, then in this nomenclature, in this particular orientation and naming and everything, then the ratio of the length of the line segments DA to DB is exactly the same as the ratio of the length of the corresponding sides CA to CB. And many times these days, especially in modernity, many people just chicken out and prove this theorem using trigonometry. But my claim is that the true understanding of anything in mathematics really comes from the combination of two things: the synthetic part of whatever it is, differential geometry, analytic geometry, theory of groups, theory of numbers, theory of graphs, whatever it is, plus the underlying algebra. And here the situation is a little bit funny or delicate, let's say, because there exists roughly, let's say, two groups of people, just for the sake of argument. One group of people likes to do things synthetically and, let's say, doesn't like or despises algebra, and conversely, the group of people who are algebraists, who love nothing but algebra, and they say, listen, whatever people you do there in synthetic geometry, let's say, is complete mystery, doesn't make any sense. This is complete nonsense and no good. Algebra is the only true way. So the thing is, my take is that no matter which corner of mathematics you stick your nose into, there is always these this partition of the way of thinking and always two groups of people. But I think that the true wisdom and the true value in investigating any corner of mathematics comes from the happy union of these two things. First, try to conduct your experiments synthetically. In this case, we will use synthetic geometry, and then carry out the corresponding algebra. And as a union of these two things, synthesis plus algebra, then you will develop a balanced and nice understanding of whatever you are doing. So to this end, we will do precisely that. First, using synthetic geometry, we will work on the proof because of this book 6 proposition 3, because like I said, the reason this is a good starting point is because this is an absolutely fundamental for understanding of how and why the definition of a circle due to Apollonius comes into existence. And now, once we understand how that works, we will prove the corresponding theorem that basically I formulated at the end of the previous segment. And we will prove it also in both ways, precisely as I claim in my view on mathematics, synthetically and then algebraically or analytically, if you will. So here, our objective, because the implication of this proposition, book 6, proposition 3, is two-sided. It works both ways: if P then Q, if Q then P. So right now, our first objective is to prove, using the machinery of synthetic geometry, that if CD is the bisector of the interior angle of the parent triangle ABC at the vertex C, then the ratios of the length of the corresponding line segments DA to DB is the same as the ratio of the length of the adjacent sides CA and CB. Here, the synthetic people will say, listen, you guys algebraists have no idea, wink, wink, what you're doing when you shuffle your symbols meaningfully left and right. Synthetic geometry is the only way. And the truth of the matter is that in the past, there were actually quite famous mathematicians who took that stance of doing nothing but synthetic geometry. One such famous mathematician was, I think, a Swiss-born gentleman by the name of Jacob Steiner. And in this respect, because I'm a nobody, I would like you to take a read on what a quite famous mathematician had to say about algebra versus synthetic geometry while I play some menacing "The Devil is Coming" music. Wonderful, and we now know that the situation even with synthetic geometry is much more complicated, it's much more involved, and in general, taking extremes in any situation is probably not very productive and a not very constructive approach. That is why, again, my personal opinion is that the best way to proceed in mathematics is to um, follow a happy balance between synthetic way of doing things and analytic way of doing things. And I give you an example. For example, in the discipline known as the theory of groups, it's even called modern algebra. It seems that algebra and symbol shuffling is the only way. Turns out this is not actually the case. Geometry can go pretty far in the theory of groups, and a lot of interesting material and a lot of deeper understanding of the underlying group structure, group factorization, on and on and on, can be achieved precisely if we take a synthetic geometry stance on the underlying matter. So here, again, to cut the long story short, we want to prove the following implication. If CD is the bisector of the interior angle at the vertex C of the generating triangle ABC, then the ratio of the length of the corresponding line segments, dA to dB, is the same as the ratio of the length of the adjacent corresponding sides that lie in the corresponding half plane with respect to this bisector. And one of the reasons we want to look at Euclid's proof is because if you can see the poetry and the elegance in Euclid's proof of book 6 proposition 3, then there is hope for you. And here there is nothing but poetry. Look at this. In order to generate this proof, what Euclid does is what's called an auxiliary construction. If the bisector CD is given to us, then Euclid constructs a straight line P that is parallel to that bisector, parallel to CD. That straight line is shown in blue, and that line is extended all the way in the plane until it intersects the line AC. Extended this way, again, we extend it into the half plane that is opposite to this half plane, logically to the right, opposite to the half plane in which the point A lives with respect to the side, let's say, CB. Again, this is not the only way. This is how Euclid did it, but you can do it the other way. There are other constructions over here are possible. We can go through parallel through the point A. It doesn't really matter. We can. There are other ways to do it, but this is one way. And here, once the straight line P parallel to CD intersects the side AC extended at the point E, we have already everything. The secret sauce, the DNA of this proof was already locked in for implications, for the two-sided implication that works. And here is the way Euclid does it. He brings in book 1 proposition 29. This is basically proposition that also two-sided proposition, works both ways. This is the proposition that deals with the angles which are formed when a straight line is falling on two parallel straight lines. And this is exactly what we have. We have a parallel straight lines CD and P, or BE in this case. And if we consider the straight line CB, this straight line, look at this, it's falling on two parallel straight lines. And in Euclid's terms, the alternate angles in this case this angle and this angle are the same according to his proof, and this is what we record over here. The angle BCD is exactly the same as the angle CBE theta. This is theta. Likewise, we have the side AC falling on two parallel straight lines. This is the side AC over here, extended, falls on the side on the straight line CD and P. And in this case, Euclid refers to these angles, if I'm not mistaken, exterior angles, but here the angle ACD, this angle, is equal to this angle right here, AEB. AEB, and this angle is theta. So now we have an undegenerate Euclidean planar triangle, BCE, with the magnitudes of the interior angles at the base, EB, equal each other by magnitude, and that means by the famous Pons Asinorum Book 1 Proposition 5, or was it Book 1 Proposition 6? In this case, the triangle BCE is isosceles on the adjacent sides CE and CB. That means that by a length, the distance from C to B is the same as from C to E. This is an important thing to us. But now, here Euclid brings in Book 6 Proposition 2. This is the proposition that he proves immediately prior to this one. And in this proposition, he claims that if you construct any straight line that is parallel to any side of the triangle and interior to it, then this parallel straight line will cut the corresponding sides in the same proportion. This is what he calls the same proportion. In this case, let's take a look at the straight line CD. The straight line CD that is parallel to this straight line P, but in this case, it is parallel to the side of the triangle ABE. We have a larger triangle ABE. Inside the triangle, the straight line CD is parallel to the side EB, and again, according to the proposition that Euclid proved just a few seconds ago, we have, since CD is parallel to EB, it follows that, look at this, AD relates to DB in the same way as AC relates to CE. And this is what we record over here. The length AD related to the length DB is the same as the ratio of the lengths AC and CE. But we just proved that CE is the same as CB, as this side over here. Beautiful, elegant poetry in action. So because of this right here, see, because of this, instead of CE, we put the CB, and boom, we have it. We omit this ratio, and we have this ratio equal to this ratio. Lettering, you can change the lettering again, dA over dB. So here, dA over dB is the same as CA over CB. This is precisely what was required to prove. Conversely, if an arbitrary point D is chosen on an arbitrary side AB of an arbitrary triangle ABC such that dA to dB as CA to CB, dA to dB is the same as CA to CB, then in this nomenclature, CD is the bisector of the interior angle of the given triangle at the vertex C. And for that proof, Euclid here reuses the same beautiful, elegant idea of snapping a straight line P parallel to that straight line. Again, don't forget that even though we know that this is not a bisector, we need to prove that CD is the bisector. Nothing can prevent us from constructing a parallel straight line. And for theoreticians in the audience, for people who like theory more than they like to solve problems, here you realize that this proof and the whole idea of defining a circle according to Apollonius is solidly positioned on top of the theory of parallel straight lines, because this is precisely what we rely on, the fact that two straight lines are parallel. This is our auxiliary construction. Here, Euclid repeats the same argument here, but we need to be careful with the flow of causality. Before, in the previous implication, we knew that these two angles are the same, but here these two angles do not need to be they are not under any obligation to be the same. So because the straight line CB falls on two parallel straight lines, we can only make conclusion about these two angles over here, theta 1 and theta 1 recorded over here. The angle BCD is the same as the angle CBE by magnitude, and we call it theta 1. From the straight line AC, we know because AC is falling on two parallel straight lines, and the exterior angles here, the angle ACD and the angle AEB, ACD, AEB. By magnitude, these two angles are the same, but we designate it as theta 2. Again, remember these two angles, theta 1 and theta 2, are under no obligation to be the same. In general, when the material is chosen at random, this is the case. But now, again, Euclid brings in book 6 proposition 2, because we still have a parallel straight line CD to the side BE of the larger triangle ABE. Still the same deal applies. We have DA to DB are in the same ratio as AC to CE, this part right here, CE to CE. So DA to DB is the same as AC to CE, precisely because in the larger triangle ABE, the straight line CD is parallel to that side we see. So, but we have, by the given premise, remember the point D was chosen at random, but in such a way that its randomness stopped at here. This relation here is honored. So DA to DB is the same, AC to CE must be the same as CA to CB. So these two parts, these two pieces must be equal, CE is equal to CB. Then it means that the triangle BCE, if CB is equal to CE, the triangle must be isosceles, and in every isosceles triangle, the magnitudes of the interior angles at the base are equal in magnitude. That means that theta 1 is identical with theta 2, and conversely theta 2 is identical to theta 1. The magnitude of these two angles is the same, and boom, voila. If these two angles are the same, that means this angle by magnitude is this angle. And what is this called? In geometry, we call this a bisector of this interior angle. So in this case, CD is a bisector of the interior angle of the given triangle at the vertex C, and this is precisely what was required to prove. On the wings of success that we enjoyed with the bisector of a planar Euclidean triangle that was interior or internal, we now wonder if we will enjoy the same success with a bisector of an angle that is external for this particular angle. And more interestingly, or more importantly, we wonder if the structure or the fabric of the proof that we just generated will transport or be the same as it was in case of the bisector of the internal angle as it will be for the proof of the bisector of the angle that is external. And the answer is yes and yes. You already know the drill, so we will go over this in an expedient manner. Here we want to prove the following two-sided implication. If we're given an external bisector in an arbitrary planar Euclidean triangle, then if that bisector of the external angle is produced enough so it intersects the extended side, let's say here AB at the point D, then it will so happen that the ratio of the lengths of the corresponding triangles will be actually exactly the same. So in some sense, algebraically or symbolically, that ratio will be expressed in exactly the same way. And this is already an interesting situation that gives us something to ponder and something to think about it, that was recorded when we dealt with the bisector of the angle of a triangle that was interior. So how will this work? Well, exactly the same way. If we have the bisector CD, by this time this bisector is of the exterior angle right here, this guy, then Euclid constructs again, well, actually, I'm not sure. I don't think Euclid proves this particular one for the external angle, but here we basically mimic what Euclid did. through the point B, we construct a straight line P that is parallel to this bisector CD. Here I named the point D in order to show that there is a lot of similarity going on, but in general, maybe you would like to see this as a different letter, D prime or whatever, but we'll take care of it. But fundamentally, the reason I kept the same naming convention and the same parallel and everything else is for you to show you that the structure of the proof for the external angle is exactly the same as it was for the internal angle or interior, exterior, whatever. So here the straight line P parallel to CD intersects the opposite side AC at the point E. You see here things in a way kind of symmetrically switch. In the previous case, the point E was on the straight line AC extended, but the point D was interior to this side AB. Here, these 2 points switch their roles. D jumped outside of the side AB, but E moved in strictly inside of the line segment AC. But the technology is exactly the same, because the straight line, you already know the drill. This because the straight line CB again is falling on two parallel straight lines, BE and CD. It means that the opposite angles, the angle BCD is the same as CBD. This angle is the same as this angle, and the same thing for the straight line AC. AC is falling on two parallel straight lines, B and CD, and that means the angle at BEC is exactly the same as, let's say, we put the angle of the point X over here, doesn't really matter. That angle will be the same as the angle XCD. So this angle is the same as this angle. But we know by the premise of this theorem that these two angles, this angle and this angle, are two exactly the same angles. So that means that these angles are the same, and that means that the triangle BCE is isosceles. This side is equal to this side. Now, there's a small wrinkle. Euclid's book 6, proposition 2, where he deals with a straight line interior and parallel to the triangle, is basically fundamental specific case. More general theorem is known these days as the intercept theorem, and I think also the mathematician by the name Thales had something to do with this theorem. Depending on how this theorem is known in your country, it doesn't really matter. The technical essence is that by the general intercept theorem in this particular setup, if we have two rays that emanate from the same point, such as the point A, and we have two parallel straight lines, then it is actually quite elegant proof. You should study it on your own or try to generate it on your own, because we have parallels, we construct heights, and the distance between the parallels is one and the same. So certain triangles in this case will have the same height, and that means that in the forward flow of causality, if parallel and this and that, then the ratios are the same. Here, the ratios of the line segments along these rays, along these sides, can be mixed and matched in any which legal way. This to this and this to this, or this to this and this to this, or this to this and this to this, and so on. Any which way this can be proven, and that is precisely what we do by the intercept theorem. We see that the distance AD, this distance, divided by BD is the same as AC by CE, this distance right here, you see. But we proved that this triangle is isosceles, so we replace CE with CB, and voila, we have this, and this is precisely what we are required to prove. And conversely, if a point D is chosen on the straight line AB extended in such a way that the ratio is given or honored, then we will prove right now that the straight line CD plays the role of the bisector of the exterior angle at the vertex C, and you already know the drill. Straight line parallel to CD. Here we again need to be careful, because according to book 1, proposition 29, we have straight line falling on parallel straight lines. You already know the drill. Theta 1 and theta 1, this angle is equal to this angle, and separately this angle is equal to this angle. the exterior angles, as Euclid calls them, and these two angles under no obligation to be the same. But here, because we still have the straight line P parallel to the straight line CD, we again use the intercept theorem. We craft the same ratio. AD to BD is the same as AC to EC. This is what follows from the intercept theorem. When we combine it with what is given, again, we conclude that the length of the line segment CE is the same as CB. Look at this. This is what's given, this is what follows, and then that means that these two magnitudes are the same, so C equal to CB. The triangle BCE again is isosceles, and it means that the magnitudes of these angles at the base of such a triangle are equal one another, and in this case that means that theta 1 is equal to theta 2, theta 1 is equal to theta 2, and what does that mean? In geometry we call it precisely the fact that the straight line CD plays the role of the bisector of the angle that is exterior for this triangle at the vertex C, and this is precisely what was required to prove. But now look at this. We proved an interesting situation in this particular case that connects together what? That connects together two bisectors. The bisector of the interior angle and the bisector of the exterior angle. And what does that mean? That means that if we merge two of the constructions that we just carried out and rename the point D that was associated with the bisector of the angle that was exterior as D prime, in order to distinguish it from the corresponding point D that was associated with the bisector of the angle of the triangle that was interior, then we will observe, or have no choice but to observe, that the angle between these two bisectors must be what? It must be right. Look at this. Phi plus theta will be equal to what? It will be equal to precisely pi radians. That means that twice phi plus twice theta is pi, factor out 2. Phi plus theta is equal to pi over 2. That means precisely that the angle D, right now I made this point X for the reasons you will understand in a second, and then D prime will be precisely pi over 2. And what does that mean? That means that these points belong to a circle whose center is located on the straight line AB extended here. I said that AB extended, and I underlined it with the red chalk in order to bring your attention to the fact that in a few minutes we will undertake an analytic analysis of the structure of the circle, and such analytic analysis shows that the center OA for Apollonius never is located inside of the line segment AB. It is always located outside of the line segment AB. So by the Thales theorem, the points D and D prime lock in what? They lock in the diameter of a circle that now carries the name of Apollonius, because this is one of the definitions of a circle that Apollonius came up with, let's say about 2,000 years ago. Again, it is important to understand that the perpendicular bisector of the line segment DD prime, and all this material, all this wonderful material, is constructible with Euclidean tools alone, the compass and the straight edge. Bisect one angle, bisect the other, straight lines, extend, produce the lines D and D prime, perpendicular bisector, marks the spot, so this will be OA. A will be for Apollonius. The center OA of the circle of Apollonius is located on the straight line AB extended, and is located strictly outside of the line segment AB. Again, an analytic analysis of the structure of the circle of Apollonius will show that this must be the case, and the points A and B, they can be called, in some sense, whatever you want to call them, two generating points or focal points, even, if you will. But this is how this circle comes into existence. And now we have a good reason, like, for example, in real time, let's say we pretend this is a process of a mock discovery. I'm absolutely sure, I do not know exactly how Apollonius did it, but I'm absolutely sure that this is not how he did it. Right now we're going through the garden path that I carefully crafted for you in order to keep the size of this episode manageable. So here is a way in which we can hone in on this definition. So now once we prove this, all these wonderful theorems, let's say using synthetic geometry, so we see that the angle between the two bisectors is precisely pi over 2 radians, 90 degrees. The angle is right. Thales' theorem, the dead center of the hypotenuse d prime is the center of the circle that houses all 3 points. But again, it is important to understand how these 3 points, d prime, and what I now call x but used to be c, how did they come into existence? Well, precisely that is how, through the specific, the equality of the specific ratios. This is what we now have. But now look at the interesting situation that we have. We proved in the previous theorems that we have dA to dB, this one for the interior angle, that was the interior situation, interior angle, this way. And for the exterior angle, we proved this situation, see? But these two ratios overlap over one and the same usual suspect. Because in some sense, if we have one ratio shown over here and another ratio over here, these two ratios are under no obligation to be the same. But because both of these ratios converge over this bridge, if you will, this ratio as a bridge, because this situation remains fixed for one and the same triangle, evidently. So these ratios equal one another. This is the important part here. These ratios are equal. We call these ratios k. In general, it can be any real number. Again, obviously, we want this k to be strictly larger than 0 to make geometric sense. And then they can be less than 1. We don't want to be equal to 1, and greater than 1. This is these are the interesting cases when this ratio is 1. Well, you should have no problem right now to say, what if dA is equal to dB, then what will happen to the bisector of the interior angle? Well, this guy will straighten out. It will become what? It will become the bisector and the height and the median of which triangle? If these angles are equal and this goes perpendicular, well, this will be an isosceles triangle. So the point d prime will run into infinity, unbuckle. This perpendicular will run parallel, obviously, this thing. And what do we call a circle whose radius tends to positive infinity in the limiting case? We call that circle a straight line. Again, I have a course called Elementary Introduction to Inversive Geometry, synthetic geometry based. If you click on the homepage of this channel, on the courses tab, you will see a course that is called exactly that, inversive geometry, blue theme. And in this course, you will learn, again, using nothing more than the machinery of a middle school, that this is precisely the case. A circle whose radius runs into positive infinity becomes a straight line. So when k is equal to 1, what is the structure of the locus of all points for which this is the case? Well, this will be perpendicular bisector. In other words, the structure of this locus, it will be a straight line. But now, besides this, in some sense, not very interesting or degenerate case, we wonder, what is the structure of the locus of the points when k is not equal to 0, and it could be less than 0 or greater than 0. In some sense, it doesn't really matter in general, but this is how we hone in on this definition. And lo and behold, this is precisely the situation that is where the circle of Apollonius emerges or comes into existence. This is how it comes into existence. And now that we have a suspicion that because of this, let's count how many. We have 2 generating points in general, A and B, distinct. Then with these points, we have our roaming point, the traveler, the runner, if you will, the point X, and the corresponding points D and D prime. And all these points are locked into a very interesting relationship. If it so happens that the ratio XA to XB is K is distinct from 1, is a constant real number, then we think that now we have our hunch that we will precisely obtain a circle, the structure of the locus of all the points in the plane that have this ratio or honor this ratio, the distances from that roaming point to 2 fixed distinct points. is one and the same, that locus will be a circle. And in order to prove or disprove our hunch, we need to prove a two-sided implication, if and only if, or the following two implications. And one way, we have to say that any point in the plane such that the ratio of distances from that point to two fixed points is the same and distinct from one belongs to a circle such that we will call that circle the circle of Apollonius, and with the subscript a, we'll designate that the center of that circle belongs to a straight line AB extended. And again, it is important to understand that this point OA is never interior to the line segment, to the generating line segment AB. It could be on one side or it could be on the other side, but it's strictly outside. Then this is the implication, and conversely, we need to say that we need to prove that any point that belongs to such a circle. And how does this circle come into existence? Well, we start with this. These 2 points are trivial to produce. If we have the circle, we simply snap the straight line AB extended, obtain 2 points, and voila, we have our ratio. So any circle, any point on such a circle will have the ratio xa to xb, the ratio of distances to these 2 generating points, the same. It will precisely be this guy right here. The first implication shown over here should be self-evident. I will not spend much time proving it because we essentially proved it already. If you rewind the previous segments, you will see precisely this is the case, with the only exception that you take my letter x, the random or arbitrary point in the plane, and rename it into the point C, what we call C over here. And this is it. After that, the proofs unfold in exactly the same way. We connect the point x with the points A, with the points B, we obtain a triangle, we snap the bisector of the interior angle, we snap the bisector of the exterior angle, obtain the points D and D prime. We already proved that all these ratios hold, and in this case we prove that the angle between these bisectors must be pi over 2 precisely, and if it's pi over 2, then Thales, circle, center. Wonderful, this implication is proved. We actually know exact, this is somewhat amazing, but we know the exact Euclidean tools only construction of the circle of Apollonius, provided of course that we are somewhat lenient with the ratio k, because in general it could be any real number that is either this or this. We exclude 1, and it could be any wild number, square root of pi raised to the power of 1 over e, who knows. But the interesting thing over here is the following fact. Rational numbers q, designated with q, are dense in the set of real numbers, and that means that between any 2 distinct real numbers there always exists a rational number. And put the other way, it is no matter which real number you give us, it is always possible to approximate that wild real number with the corresponding rational number within the delta. In other words, if rho is a real number minus rational number can be made less than epsilon, and epsilon is an arbitrary, strictly positive real number itself. So this is one way to interpret the fact that the set of rational numbers is dense in the set of real numbers. We can use rational numbers to approximate real numbers fairly well for our practical purposes. If it's a rational number, so we have m over n, 5 over 3, 3 over 17, 21 over 19, whatever it is. And once we have that, and already that's it. Euclidean tools only construction unfolds naturally. We know how to do all this. And look at this. The point D corresponds to the division of the generating line segment AB in the ratio m over n or k internally. And the point D prime corresponds to the division of the generating line segment AB in the same ratio m over n or k externally. So far so good, but now for the converse implication, if we grab any point x on the circle of Apollonius, which was constructed which way? Well, snap a line, divide the line segment AB internally, externally with the straight line, cut the line segment in half, and have this ratio locked in. Then we are to show that the ratio of distances from that point to A and B is precisely the same K. This is what we need to show. And for a synthetic proof, in a few seconds we will do an analytic proof also, but for a synthetic proof we need to do a little bit of work. The proof of the converse statement in this case is not particularly difficult, and given the fact that we went through the previous proofs in detail with the synthetic geometry, in certain sense, the tactical maneuver or a tactical maneuver that will be helpful in this application, we already went through it. Remember that Euclid in both cases, in book 6 proposition 3, constructed an auxiliary parallel straight line. So which such parallel straight line will have over here? Well, for example, a straight line P parallel to the straight line AX. In other words, in this application, to start from the beginning, we're given two distinct points A and B. These are our generating points, the corresponding line segment and the corresponding straight line, and we're given a circle of Apollonius. And how was this circle constructed? Well, we know that we divide the straight line, the line segment AB, internally in the given ratio. We divide that line segment externally. When we do so, we obtain the points D and D prime. We cut the line segment D prime in half, obtain the center OA. I don't want to pollute the namespace over here, but yeah, let's say the center OAA for Apollonius. We snap the circle. This is how we obtained it, and then we pick a point X on that circle at random, or let's say an arbitrary point such that it is neither D nor D prime, because for points D and D prime it is already clear what's going on. This is how in some sense we obtain that circle. Now our objective is to show that the distance, the ratio of distances from X to A and from X to B, I show this straight line over here dashed, is exactly K, exactly the same as was used in order to produce the points D and D prime, and thus generate this specific circle of Apollonius. So this is the premise, this is the input, and the output supposed to be what? Well, the output, we need to show that the ratio XA to XB is precisely K. And the way we do it, one tactical maneuver that helps over here, this is K precisely. One tactical maneuver that helps over here to unlock an elegant proof of this theorem is the following. We construct, again, we connect all the points, we connect the arbitrary point X, distinct from D and D prime, with the points A, D, B, and D prime. We have our straight line, AB extended. So now what we do is the following. We construct a straight line, lowercase p, parallel to the straight line AX. You see, no matter where the point is will be, we'll lock it in, take our Euclidean tools, and construct a straight line shown in blue over here that is parallel to AX. P parallel to AX, AX parallel to P. This is what I recorded over here, P parallel to AX, and pretty soon we will call it KT. Where did the points KT came from? P intersects the straight line XD extended over the point K, and P intersects the straight line XD prime at the point T over the single point T. This is the point right here. And now once you generated this idea to construct this auxiliary line, the rest of the proof basically flows without any problems. Look at this. Let's concentrate on these triangles. ADX or DAX and DBK. What can we say about this triangle? Look at this. The interior angles at D for these triangles are vertical, and hence by the corresponding theorem are the same. Book 1, proposition 29, straight line AB falling on two parallel straight lines, P and AX. What does that mean? It means that this angle shown in yellow is the same as this one by magnitude. Consequently, we have the straight line XK falling on two parallel straight lines, P and AX. And what does that mean? That means that this angle shown in green and this angle shown in green also the same by magnitude, by angle. Let's put it this way. I will write it down for you in a different color so you can see by angle, 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 the triangles DAX and DBK are similar. Wonderful. And book 6, proposition 4, if I'm not mistaken, in equiangular or in similar by modern terminology triangles, the length of the ratios of these sides of these triangles about equal. Angles are the same where the corresponding sides lie opposite equal angles. That means that the ratio of the length AX to AD, look at this, AX that lies opposite this angle to AD that lies opposite this angle is the same as the ratio BK. BK lies against the same angle, and BD. BD. This side lies against this angle corresponding to over here. And once we, what did I do over here? I moved AD to the top over here and BK down here. You see, like this. This is a legal maneuver. So AX over BK is the same as AD over BD. And we manufactured 1/2 of our ratio already. This is K. So AX to BK is K. Remember, we simply swap these two guys. Denominator on the right hand side into the numerator on the right hand side into the denominator, and the other way, denominator from the left hand side and the numerator on the right hand side. That's a game over. Likewise, we have another parallel straight line lurking in the midst of this material. This is parallel to this, so we now have two more triangles. Let's concentrate on these ones. AXD prime and BTD prime. You see, AXD prime, AX prime, AXD prime, or D prime XA, and D prime TB. These triangles are also similar by what? By angle, angle, angle. Same angle, same angle. We have this side over here, shared angle, and then this angle will be equal to this angle. And by the way, once we pick a point X distinct from these 2 points D and D prime on the circle of Apollonius in an arbitrary fashion, the angle D X D prime will be what? Right by the Thales theorem. We have this in the bank. So now from the similarity of these triangles, D prime X A and D prime T B, we have the following ratio. D prime X is similar to D prime TB by the same angle, 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 to make sure that we're all on the same page. And then look at this, BT to BD prime. BT that lies across opposite shared angle to BD prime must be in the same ratio as AX that lies against shared angle. And which side was it? XA and AD prime, this side right here, because BD prime lies again opposite this angle, and the corresponding angle for this is this guy, so we must take AD prime. So BT over BD prime is the same as XA over AD prime. Trivial. And then again, we want to move AD prime over here, BT downstairs, and we have AD prime to BD prime, which is K, is XA and to BT. See, that's the thing. But we know that the points D and D prime are not just random points in the plane. They were picked specifically for us to generate the circle of Apollonius. So this is K and this is K. So if we have one and the same real number that is equal to this ratio and this ratio, it means that these two ratios are the same. XA over BK is the same as XA over BT. See, XA over BK is the same as XA over BT. That means that BK is equal to BT. BK is equal to BT. Let's find this, guys. BK to equal to BT, this. But this is the observation. The triangle KXT is what? That triangle is right, because remember, the angle in the semicircle is right. This is the theorem due to Thales. So the triangle KXT is right. And in this triangle, we have the point B. We have the point B. Since BK is equal to BT, and these points are collinear, it follows that B is the midpoint of the hypotenuse KT. It's the midpoint of the hypotenuse KT. And what does that mean? If we have a dead middle of the hypotenuse, which is the point B, that means that this point again by the Thales theorem, if you will, is equidistant from the following three interesting points. It's equidistant from K, T, and X. This is the center of its own circumcircle for the triangle KXT. Game over. So once we have BK equal to BT equal to BX, which is XB, this is what I recorded over here. See, this is BK is BT is XB or BX, no matter how. This is the property, actually fundamental property of a metric. From A to B and to B to A is the same thing. So now into our ratios over here, we replace BK with XB. We can do it because of this. And in this ratio, we replace BT with XB because we can do it. See, XA to XB, and over here, XA to XB. And this is precisely what we have. Look at this. DA to DB is in the same ratio as D prime A to D prime B, and in the same ratio as XA to XB. This is what we call K M over N, a rational number for nice and beautiful Euclidean tools only construction, and this is precisely what was required to prove. So now let us wrap our brain around what we just proved. We just proved that if an arbitrary point in the plane X is such that XA is equal to XB, then that point belongs to a circle that has the property that the points D and D prime, like that, the center of that circle is located strictly outside of the line segment AB, but on the straight line AB extended. And conversely, if we take any circle that was constructed that way, where the point D divides the generating line segment AB internally and D prime externally, then any point on such a circle will have the ratio of its distances to two generating or focal points A and B precisely the same as dA to dB and as D prime A to D prime B. So now that we proved this result synthetically, let us go over an analytic proof of the same thing. And like I said before, there is no reason to, in my personal and humble opinion, there is no reason to dive into any extreme. I think a solid understanding of any subject matter comes from a happy union of two lines of reasoning, synthetic and algebraic. And analytic expression that we will obtain in a few seconds also allows us to conduct a fairly rapid analytical, again, research of what happens when the ratio K over here, the ratio K approaches 1. Negative infinity. An analytic proof of the fact that the structure of the locus of all the points in the plane such that the ratio of distances from each point of this locus to two fixed distinct points is really a circle that has its center on the straight line AB extended is very straightforward, even though technically this is the apparatus of analytic geometry, but the underlying mathematics is nothing beyond the capabilities of an upper middle school student. There are no determinants, no groups, no anything fancy. It's just middle school arithmetic, and this proof unfolds in the if and only if implication, and that is why we can do it in one segment. So here, in many texts, or pretty much in any place that you will look at, many authors will place the origin of their coordinate system into one of the points, and here, to deviate from the majority, I will place it in the middle of the 2 points. So in other words, the distance AB is taken to be D, a strictly positive real number, a strictly positive real number. And again, you can experiment with other coordinate systems types. Maybe you can try to swing the same proof in the polar coordinate system. This is a traditional classical Cartesian coordinate system, orthogonal axis. Origin is placed in the middle, in the dead middle of the line segment AB. So in other words, the coordinates of the points A and B in this way chosen coordinate system will be minus d over 2, 0 for A and plus d over 2, 0 for B. Now we take any point in the plane, we'll call it P. Naming it X is not really convenient because we will be dropping an orthogonal projection of this point on the X-axis. We'll call it PX, which is a stand-in for X. we will drop a perpendicular or orthogonal projection of the point P onto the y-axis, Py. This is a stand-in for y. Xy are the coordinates of such a point, and all we have to do now is unfold this into an analytic story. And the way we do it is like this. Look at this. Look at the upper left side over here, or maybe I'll stand over here on that side. It will be more convenient. So we're given, this is the premise, this is what we are given, this is the starting point of our analytic symbolic shuffling, if you will. PA over PB is K, a real number that makes sense, and it's not 1. We will consider the case of 1 at the end of this manipulation. So this, if this is true, then the following implication is also true. This is true if and only if P A is equal to K times PB. We basically unfold this ratio into a product. And this is true if and only if we square both sides. Again, this works because the square root function is continuous, monotonically increasing, so everything is good. We work with distances, strictly positive real numbers. So once we square this, now just about the only technical maneuver that you need to execute over here is apply the Pythagorean theorem twice to which triangles? A PXP and B PXP. Game over. You spell it out. A PX squared plus PPX squared, and then B px squared plus ppx squared. These are the squares of this hypotenuse, is the distance PA and PB. That's it, game over. There is nothing really complicated over here. Now you take the distances, even though the coordinate for the point A says minus d over 2, the distance is what? X plus d over 2. So that's what we write. X plus d over 2 squared plus y squared. Ppx is extended for y. Is equal to k squared times what? Now be careful over here. This distance over here will be what? Is x. But this distance, bpx right here, is what? X minus this. And what is this? D over 2. Again, even here in the world of analytic geometry, still we're using some basic synthetic geometry, if you will. And this point can be, we can argue, it can be located here or here or here. It doesn't matter. In theory, pedantically, yes, we need to cover all quadrants, but what you will see is that no matter where the point P is located, you will always have the structure of your equation like this. There will be sum on one side and the difference on the other. Let's say you move the point P from this quadrant to this one. Well, here you will drop the perpendicular on the x-axis, and for this guy you will be subtracting, and for this guy you will be adding. Game over. So the claim is that the structure of this equation will always be the same, no matter which quadrant the point P is in, and off you go, roll. If and only if you open up the squares, x squared dx, d squared over 4, y squared, the whole thing on the right hand side. I hope I didn't make any mistakes, but again, if and only if. Now what we do is this. We grab all this material and move it from the left hand side to the right hand side. Look at this. K squared x squared minus x squared becomes what? K squared minus 1 x squared, and this is it. This is the guy right here, minus d times k squared plus 1 times x plus k squared minus 1 d squared over 4 plus k squared minus 1 times y squared. Again, this is symbolic shuffling. This is the devil is coming music that you heard at the beginning of this episode, courtesy of the famous mathematician whose name you saw. Now, because k right now we take is not equal to 1, we divide this through by k squared minus 1. Exactly. What do we have? Vanishes k squared minus 1 from the left, x squared. Here the k squared minus 1 goes into the denominator of this guy. The k squared minus 1 by y squared vanishes, and I move the d squared over 4 over here. Complete the square on x, and voila, we have our equation that captures the analytic structure of the locus of the points in the plane such that the distance from each point that belongs to the locus, the ratio of the distances from this point on the locus to two fixed distinct points is k. This is it. This is our equation. More details to drill in for those who still want to know how this is done. Again, I do not repeat this often enough, but it's a good idea for you to put this video on pause, walk away, carry out your own computations, come back and compare your results to mine. Keep me honest. If I made a typo somewhere, I apologize. But the idea is this. Look at this. D times this animal can be represented how? 2 times d over 2. 2 cancels out, but we need this to manufacture the complete square. So once we slug in the square of this guy plus this, we need to subtract it. So there will be minus the square of this term. But now we carry it to the right hand side over here. So on the right hand side of the equal sign, we will have this animal minus d squared over 4. D squared over 4, d squared over 4, carry out. Here's minus 1, open the squares. K to the fourth plus 2k squared plus 1 minus, look at this, this is minus and this is minus. So minus k to the fourth plus 2k squared minus 1. And to make sure that you catch this, let me show you. K to the fourth and k to the fourth cancels out. Plus 1 and minus 1 cancels out. What do you have? 2k squared, 4k squared. 4 in the numerator, 4 in the denominator cancel out. And this is what you have. Square, square, square. Everything is squared. Wonderful. So now we make the conclusion. The center, OA, of the circle of Apollonius is located at the coordinate which has which components. This is for the x, 0 for the y. You see, this is our claim that we made in synthetic geometry, that the center of the circle of Apollonius is always on the straight line AB extended strictly outside of. And you can carry out this analysis over here to see that the coordinate will always step over d half. Whether this thing is positive or negative. Can it be negative? I guess it can be if k is less than 1 over k, but that's an interesting, again, on your own. Do this, replace k with 1 over k and see what happens with this. All the circles basically travel with respect to the bisector of AB to the other side, and this gives birth to the so-called pencil of circles of Apollonius. Separate issue. And what's the radius? Well, we simply read it off of our analytic expression. This is the center, this is the radius, since this is squared. So what do we have? K times d over absolute value of k squared minus 1, because k could be less than 1 or more than 1, but evidently radius is the distance. The distances cannot be negative. They have to be 0 or positive. So we put the absolute value. And now this brings us to the question of what happens when k is equal to 1. Well, let's do what all mathematicians do in this case. Take the limit out of this thing when k tends to 1. When k tends to 1, the radius of this circle of Apollonius tends to what? Tends to positive infinity, because the denominator here always remains positive. Look at this, absolute value, always positive, and in some sense, this is how it should be. So now we know when the radius of a circle tends to positive infinity, then how does it change? How does the structure of this object changes? Well, it becomes, in the limit again, it becomes the straight line. So this is an analytic proof that this is the straight line, and then boom, the bisector is the locus. Now, we cannot do this analysis for the center of the circle of Apollonius like this, very crude analysis, if you will, because now it's important exactly how k tends to 1, from the right or from the left. Now, if k tends to 1 from the right, maybe I should write it in red for you so you can see it over here. That means that if k tends to 1 from the right, what does that mean? That means that k remains greater than 1 at all times. You see, this is the designation, 1 raised to the power plus. K tends to 1 from this side right here, again, geometrically. So this denominator always remains what? If k is greater than 1, k squared is greater than 1, k squared minus 1 is strictly positive. So this center tends to positive infinity. So the center of the circle of Apollonius, in this case, runs away into the positive infinity. But if k tends to 1 from the left, in other words, approaches number 1 from the left, it means that it always remains smaller than 1 or less than 1. It means the square of k is even smaller than 1. K squared minus 1 is less than 0, so the denominator here is always negative. So in this case, the center of the circle of Apollonius runs away into negative infinity to the other side. So now you understand this limiting situations. And again, that is why I say that instead of jumping into extremes, it is always a good idea to have a balanced and combined understanding. Synthetics and analytics. Merge them together, you're in good shape. So now we understand how the circle of Apollonius comes into existence, and now that we understand, we can step up to the problem and see how we can generate the problem of equiangular orbit from each point of which both the Earth and the Moon are seen under the same angle. Circle of Apollonius. Well, anytime when I solve a problem, any technical problem, I always try to see if I can animate the subject matter in this problem. Most of the time, I simply do not have enough time to carry out the animation, but sometimes when I do, I gain a deeper understanding of what is going on. So there are many ways to develop a better, more intimate knowledge of the problem you're dealing with. So now, before we jump into the Earth-Moon equiangular orbit problem, I would like you to take a look at a small animation that I put together for you using the free software called GeoGebra. And in that animation, you will see the following. This overall material that we covered in this episode can again be animated in a number of different ways, but my mind was working as in the following direction. Let's say we have 2 points, A and B, right? And we constructed, centered over here is the circle of Apollonius. Any point that you will see running over here, what will happen? What's one way to develop some maybe visual intuition for this? Well, if we construct a triangle with X as a vertex and construct the bisectors of the angle, you see this angle by magnitude will vary, obviously, right? As the point X travels over the periphery of the circle of Apollonius, the magnitude of the angle AXB will vary. So in that sense, the behavior of the bisectors of the exterior and interior angles will also vary in some perhaps wild way, but that is not the case. You will see in the animation right now that these points over here remain where they are, or in some sense the internal and external or interior exterior bisectors, they point precisely to the points D and D prime, our proverbial points in all these proofs, and they do not move anywhere. In other words, imagine you hop on a circle and you have two laser lights, and no matter how you move over the circle, your laser lights will always point you to this points D and D prime at all times. So here's animation. It's about 30 seconds. Please take a look. Wonderful. And now that you saw the animation, you saw how I was thinking. And when you see the point X, what does it do? When you see the point X orbit the points A and B in a certain way, then what comes to mind? Well, remember my hint. What is a point? A point is what in the previous life, the point was a circle. So we have two limiting conditions over here. One, the limit when the radius of the circle tends to positive infinity, then the circle becomes what? Straight line. And then the second limit, when the radius of the circle tends to 0, then the circle becomes what? A point. Exactly. So the points A and B, this is what you see. These are the points because they are the points right now. But in their previous life, these points were circles. Wonderful. So circles used to be what? Circles used to be spheres, and spheres used to be planets, and thus the problem is born. How do we construct, or what is the shape of the orbit from each point of which the Earth and the Moon, let's say, is seen under the same angle? It should be understood that at every point of that trajectory, instantaneously at this particular moment, compared to the next one or the previous one, the magnitude of this angle will change. But at that instance, both angles should be the same. And here some people may say, Roman, look, you told us that we need to come up with a problem that is based on a definition of a circle. You gave us some funky hint. Well, what's the point? Is it a circle or is it not a circle? Well, we can construct, now that we know how the circle of Apollonius works, we can construct all sorts of gazillion of different problems. Here is one. construct a triangle given its base A, the height HA that drops on there, and the ratio of these two sides, of the remaining sides. So we're given A, height, and the ratio of B to C. Well, this is exactly the proof that the proofs that we generated. We basically divide the line segment internally and externally to obtain the points D and D prime. Based on this is our K. We know what's going on. And after that, cut in half, circle, and then snap two straight lines parallel to A, distance HA, this way and this way. And voila, we have 4 candidates. So this is our, these are our circles. There you go. That's a problem that is based on a definition of a circle. Why not? Well, this is the crux of the matter. This is why I put this episode together, because in this particular problem, construct a triangle given the base, the height, and the ratio of the lengths of two sides. The circle of Apollonius unlocks an instant solution, elegant, crisp, wonderful. But this is very, this problem, the fiber, the texture, or the fabric of this problem is very immediate. It's very down to earth, so to speak. It treats every object that we considered so far as it is. Points, angles, distances, nothing. This is a nice problem. This is a legitimate candidate, but that is the issue with, the situation with constructing problems. Given the same input material, the problems of different texture can be constructed. So that is why I said that in this episode we can only acknowledge the existence of this huge technical layer of construction of problems, because there are way too many nuances. So here with this problem, we in a way try to pull the problem solver away from the immediacy of the suggestion that there is a circle of Apollonius is involved over here. When you ask your students, for example, what is the shape of a trajectory from each point to which both the Earth and the Moon are seen under the same angle, how does this smell like a circle of Apollonius? Not at all. But we now know how this works. So this is the process of constructing a problem. Look at this. The circle is, among other things, also known as a curve of constant width, and we've dealt with curves of constant width on this channel before in season 2 with the so-called rouleau triangle. And in this case, if we fix the distance from the center to an external point, anywhere from that point, the circle will be seen under the same angle, and this angle is always well defined as long as the point outside. How we define this angle? Snap two tangents to the given circle through the given point. The angle is theta. This distance, this angle will be cut in half if we connect the point with the center. So here we go. The trigonometric function of sine of theta over 2 is defined as radius of the circle, r divided by the distance from P to O, center distance, if you will. So in our problem, the way our mind works is as follows. If this angle must be the same, and again, if you plot sine of x and sine x of over 2, you will see that on the appropriate interval from 0 to pi, our function will grow nicely monotonically somehow to pi over here like this. This is all taken care of. Wonderful. So the ratio of the radii, look at this, the ratio of the radii of the moon and the Earth, well, let's say the ratio of the radius of the Earth to the radius of the moon must be the same as the ratio of the distance to the center. DE is the distance to the center of the Earth. dm is the distance to the center of the moon from any point on our mystery trajectory. But if this ratio is what it is equal to the ratio of radii, and this is constant. We take that the radius of Earth and the radius of the moon is constant, and this is our ratio. Okay, that's it, game over. We instantly know what the solution is, and we can even use the Euclidean tools to construct it. In season 2, again, early in season 2, I will find the episode numbers for the rouleau triangle, and for this problem they will be in the comment section. Check them out. We explain how to construct internal and external tangents to two circles that have different radius. And look at this. Internal tangents in this case Earth, Moon will intersect at the point D that will precisely divide this point, divide the distance between the Earth and the Moon in the given ratio like this internally, and the external tangents to these two circles will intersect at our point D prime that divides again the distance between the centers of the Earth and the Moon externally. There we go. Cut this distance in half, snap a circle. This is the orbit. The orbit is a circle of Apollonius, and in some sense we can call it even the orbit of Apollonius, if you will, in this case. And this is how mathematics works, on and on and on. Here we constructed the orbit that is based only on a metric component, so to speak. But we can ask other questions. What is the surface? What is the surface? From each point to which, not that every celestial body is seen by the same angle, but from each point to which the pull, the gravitational pull by each celestial body is equal on this. This is called the Lagrange surface. This is a different story. But now, take a look at this. We understand how these things work. And then if we, this is a planar orbit, this is a planar orbit, but how do we decide which plane is it, which plane is good? Well, there is no way to decide. All planes are good. So if we now rotate our contraption by pi radians in space, then what will happen? The circle will actually sweep with both of its halves a sphere. And in this case, it will be a, we can call it a sphere of Apollonius, and from any point on that sphere, amazingly enough, we will see both the Moon and the Earth under the same angle. And this, all this information comes from here. Now that you understand how these things work, I will take a second to erase this material, or maybe I'll write down the numbers. But for specific numbers, we want to see realistically, how does this orbit look like? Where is Earth, where is Moon, what's going on? Remember, the analytic or mathematical, not physics-based, but a mathematical analysis of the situation tells us that the center of that orbit will always be, let's say, to the right of the center of the Moon, somewhere here, strictly outside the line segment that delineates the distance between the centers of the Earth and of the Moon. And now for some specific numbers. 916 kilometers, and this is how things usually work. By the time you arrive at the point where the real fun begins, you run out of time. We need to keep the size of this episode manageable, but you can see that an enormous amount of interesting mathematics is spawned, and even we can argue, okay, is this a problem? What do you think? Is this a problem on physics, or this is a problem on mathematics? Maybe it is a problem on physics because here we use the words such as celestial bodies, Earth, Moon, orbit. Well, underneath we see that it's really a problem in mathematics, and this spawns in other problems in physics. For example, this is the surface. Let's say sphere of Apollonius is equiangular surface, but what about equigravitational surface? What will it look like? What is the surface between the Earth and the Moon, such that on every point on that surface, the gravitational pull from both the Earth and the Moon is exactly the same? That's another interesting question. All sorts of wonderful mathematics blossom out of it. But anyway, we do not have much time. So let's say I take the radius of Earth to be 6,000, roughly, again, approximately. All these nitpickers of the world, please take it easy. 6,371 kilometers. Again, approximation of Earth by a sphere is not exact. It is not a perfectly sphere, but for our experiment, for our purposes, from far away, it's sphere enough. The radius of the Moon is taken to be roughly or approximately 1,737 kilometers. The distance between the Earth and the Moon is taken to be approximately 385,000 kilometers. Again, all the pedants in the world, take it easy, breathe, relax. This is good. We all know that the Moon orbits away from the Earth. This linear displacement is small, as about inch or a couple inches a year or something like that. So this is not pedantically strictly true, but again, for our experiments, we'll take it to be fixed, even though it is not. And then if we crunch the numbers through the formula that you just saw a few seconds ago, it comes out that the radius of the orbit of Apollonius for the Earth-Moon pair will be 130,396 kilometers. Not that I have a good sense for these numbers, but this is what mathematics says. And the center of the orbit of Apollonius for Earth-Moon pair is 415,916 kilometers away from the center of the Earth. I did the displacement. You can actually crunch the formulas yourself if you place the origin of the coordinate system into one of the points. Again, the radius obviously will come out the same, but the location of the center will be a little bit different. I think you will have k squared over there. It doesn't really matter. You have the half distance, move it by half, the distance between them, half of this distance, voila, you have it. 415,916 kilometers. Again, because the radii of both of the celestial bodies, the Earth and the Moon, are so small compared to their distance in the average household conditions that it's simply impossible to give a proportionate, realistic construction of the orbit of Apollonius for the Earth-Moon pair. But what I did for you guys is the following. I took this distance right here, will be 1 unit. And then I crunch the numbers, so we basically divide the radius of the Earth by this, we divide the radius of the Moon by this, it comes out minuscule numbers, but then we divide these numbers by this, and then it becomes reasonable. And this is how precisely the Earth-Moon Apollonius orbit will look like. Please take a look. Very good. This will be it for the mathematical problem S3M25, and we will move on to a new challenge next. Our next challenge will be a problem in physics, S3P11. We continue to study the initial area of physics called kinematics, and in this problem, we're given a circle of radius r. A circle of radius r here I designated with the uppercase r because lowercase r in physics is always taken to be the radius vector of a point that is executing a certain motion, so we do not want to clash or collision with the name. So uppercase r is the radius of the circle, c is the center of that circle, and a units away from the center of that circle there is a point O, about which, see, not about C, but about which the point P on the circle is rotating with a constant aerial velocity. The constant aerial velocity, sigma 0, it is given to us. And what does that mean? That means that in equal amounts of time, with respect again to the point O, the radius vector OP will sweep equal areas. And here again, the constraint on A, that is, A is less than R. And in some sense, we can say it's greater than 0, but again, it's always interesting to figure out what will happen in the limiting case when A is exactly 0 and A is exactly R. So the objective of this problem is to find the velocity V of the point, the velocity of the point P as a function of the distance of that point from the point O. Like we designate this distance as rho. Then as a function of this distance, we want to compute the velocity of the point P. And speaking of the process of constructing problems, once you solve this problem, try to see if you can construct a sister or a sibling problem that basically does something similar to the problem to the setup that is given in the problem S3P11. Now, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the physics problem S3P11.